Have you ever wondered what silence sounds like on another world? Imagine standing under a salmon-colored sky where the horizon never ends. The air is thin, and every grain of dust carries the memory of ancient rivers. Mars doesn't shout its story. It leaves it in traces: dry channels, mineral veins, faint whispers in the wind. Each rover that rolls across its surface adds one more line to a diary written in rock and light. For scientists, every image, every signal is a clue to what the planet once was and what it might become again. If you enjoy exploring these quiet frontiers with us, a gentle like and subscribe helps others find their way here too. Settle back and listen closely. Mars is about to speak. Mars is a small, dry world that has held human attention for a very long time. Its steady red light made early observers mark it on their maps and fit it into their calendars. Myths followed, but the real planet is more careful and more complex than the stories. When we look closely, we see frost forming on dunes at dawn. We see wind moving dust along gentle slopes. We see channels cut by water that is now gone. There are canyons wide enough to stretch from horizon to horizon, and mountains that rise so high the air, already thin, becomes almost nothing. The sound here is quiet, and the changes are slow, but the signs are clear and readable. As we walk through these signs, we can explain how Mars formed, how it changed, and how those changes relate to Earth. The same physics shapes both worlds, but size and time led them down different paths. Machines have gone first to survey the ground. Rovers on wheels, landers with drills, and small flyers that tested the air. They look, they measure, and they send back data that lets us turn pictures into knowledge. This is not only a list of facts about a cold planet. It is a careful record of a neighbor that has shared our sky for as long as there have been people to look up. Step outside on a clear night, and Mars appears as a steady point of rusty light. Most stars sparkle white and flicker. Mars holds a warmer tint, red-orange, like iron that has been left to weather because iron-rich dust on its surface and in its air reflects sunlight in that way. To the eye, this color stands out. Long ago, before lenses and cameras, it was enough to make people pay special attention. They also saw something else. The stars keep their patterns as they rise and set, but a few bright points wander slowly against that fixed background. These are the planets. Mars is one of them, and its path is not a straight slide across the constellations. Most of the time, it drifts eastward. Then, for a few weeks, it seems to slow, stop, and move backward toward the west before moving forward again. This is retrograde motion. Retrograde means moving the other way. It is a trick of viewpoint. But without that idea, it looks like a puzzle. Ancient observers did not have the concept of orbits the way we use it now. They placed Earth at the center and tried to make the observed loops fit that frame. To do this, the astronomer Claudius Ptolemy used circles on circles, called epicycles. In his model, Mars rode a small circle whose center moved along a larger circle around Earth. With the right sizes and speeds, the loops in the sky could be predicted. The math could match the view, but the structure was heavy and hid the simple reason behind the loops. Much later, Nicolaus Copernicus put the sun at the center. In that layout, the retrograde motion becomes a normal result of two planets moving at different speeds. Earth is closer to the sun and moves faster. When Earth passes Mars, the line of sight swings so that Mars appears to drift backward for a short time, the way a slower car seems to slide backward as you pass it on a highway. The planet never truly reverses. It only looks that way from where we are. Even without telescopes, careful observers tracked these changes with surprising accuracy. The Maya recorded Mars's shifts and could forecast where it would be months or years ahead. Scholars in India kept detailed notes on its position relative to the constellations. These efforts were not just for curiosity. They connected to calendars and to social life. The color and speed of Mars were often read as signs. The links to war came from that deep tint, not from anything the planet did. Still, the sky made people look, and looking led to records, and records led to better models of motion. In the early 1600s, Galileo Galilei used a telescope to look at Mars. His view was limited by the small lenses of his time, but he could see a disk, not just a point. That was enough to show that Mars is a world with size and a surface. A few decades later, Christiaan Huygens drew a dark feature, we now call it Syrtis Major, and watched how it turned in and out of view. From that, he estimated that a Martian day lasts a little over 24 hours. He was close to the modern value of about 24 hours and 37 minutes. Knowing that Mars spins at almost the same pace as Earth gave observers a new sense. Day and night are not special to us. They happen there too. As lenses improved, maps of Mars became more detailed. Observers noted white caps at the poles that waxed and waned with the seasons. This hinted at ice. They saw patterns on the surface change with dust storms that can grow to cover much of the planet. These real changes opened the door to guesses that went too far. In the late 1800s, Percival Lowell described long, straight lines he thought he saw and called them canals, as if they had been built to move water from the poles to drier zones. Our eyes like straight lines, and our minds like order, but later, sharper imaging showed the lines were an illusion. Still, the idea pushed people to pay closer attention and to plan better tools for viewing. Before these tools, Mars had already taught us one core lesson. The sky is not fixed. The planet brightens and fades with distance, draws loops through the constellations, disappears behind the sun, and returns on schedule. Watching it do this ties human time to orbital time. The pattern is steady, but it is not simple. Learning to follow the path of Mars helped us learn to think in terms of orbits, speeds, and angles. It also helped us place Earth where it belongs, as one planet among many, rather than the center. Go back about 4 billion years, and the solar system was a cloud of gas and dust around a young Sunday. In that cloud, small grains stuck together, turning into pebble-sized pieces, and then into bodies big enough to pull in more material by gravity. These are planetesimals. When many planetesimals merge, they form protoplanets. Mars formed in a zone with less material than the region that fed Earth. With fewer building blocks, it grew smaller. Its diameter is a little over half of Earth's, and its mass is about 1/10. In planetary science, size matters because it controls heat. Larger planets hold heat longer. Heat inside a planet drives a molten core, and with motion of metal and charge, can maintain a magnetic field. A magnetic field shields an atmosphere from the solar wind, which is a stream of charged particles from the sunday. A small world cools faster. Its core slows. Its field weakens and can shut down. Then the solar wind can strip away air over long periods. The early Mars was not quiet. Volcanoes were active across the surface. Some grew to extreme size because the crust did not move the way Earth's crust does. On Earth, the outer shell is broken into plates that slide over the mantle. These plates move over hot spots, and make chains of volcanoes. Think of the Hawaiian Islands. On Mars, there is no plate motion like that. So a hotspot stays under one place and can build a single volcano for a very long time. Olympus Mons is the largest example. It rises about 3 times the height of Mount Everest and spreads over an area about the size of a large country. Nearby, shield volcanoes line up across a region called Tharsis, which is a giant uplift in the crust. These features show how strong the early heat flow was. Impacts shape the surface as well. The first few 100 million years were a time of heavy bombardment throughout the solar system. Asteroids and comets hit often, carving out craters of many sizes. In the north, a vast lowland called the Borealis Basin may be the scar of a single huge impact. If so, one event changed the top half of the planet's shape and helped set up the contrast between the southern highlands and northern plains. Impacts are destructive, but they also affect climate and geology. A very large impact can release enough heat to melt ice, thicken the air for a short time, and drive water across the ground. From orbit, we see valleys, networks of channels, and delta shapes, where water once slowed and dropped sediment. These features suggest that liquid water flowed at the surface more than once, maybe in bursts linked to volcanoes and impacts, and maybe for longer periods during warmer climates when the air was thicker. Inside the planet, heat from formation and from radioactive decay kept rock partly molten at first. Over time, the mantle cooled and stiffened. The crust thickened. Without plate tectonics to recycle rock back into the mantle, the surface kept its old features. On Earth, rain, wind, ice, volcanoes, and moving plates erase and rebuild landscapes. On Mars, many landscapes remain in place for billions of years. A dried riverbed or an ancient shoreline can still be traced. Lava plains hold the shape of their flows. Craters keep their rims unless they are filled by later events. This preservation is one of the reasons Mars is such a valuable record of the early solar system. Volcanism did not stop all at once. Evidence suggests that some lava flowed in geologically recent times, possibly as late as a few million years ago. Geologically recent means recent on the timescale of a planet, not in human terms. It hints that heat remains in pockets and that the interior is not fully cold. There are also signs of young landslides, fresh-looking crater ejecta, and recurring dark streaks on slopes that may involve briny water moving just below or at the surface under special conditions. Each of these clues must be tested with care, but together they show a planet that still changes, even if the changes are slow and local. Early Mars likely had a thicker atmosphere, with more air and more greenhouse warming. Water could have stayed liquid at the surface. Clouds could have formed, and snow could have fallen in colder regions. As the interior cooled and the magnetic field weakened, the solar wind stripped gas away more easily. The air thinned. With less air, heat escaped more quickly and the surface cooled. Water either froze in the ground and at the poles or moved underground. Today, most of the water we can point to is locked as ice in the polar caps and as ice mixed into soil at middle and high latitudes. Some water also exists as vapor in the thin air, and thin frosts can still form when temperatures drop at night. When a planet cools and dries, its active cycles slow or stop. On Earth, the water cycle is strong because heat moves water from ocean to sky and back again. On Mars, that cycle is weak. Winds lift dust more often than they move water. Even so, the loss of activity preserved the old scenes. Where Earth's crust is young in many places, Mars has wide regions that are ancient. This makes the planet like a library where old books were never cleared from the shelves. Researchers can read the sequence of events if they map carefully and date surfaces by counting craters and comparing overlapping features. The orbiters and rovers we have sent let us read those pages in detail. Cameras measure shapes and textures. Spectrometers break light into bands that show what minerals are present. Radar probes the ground to look for buried ice and layers. Landers and rovers test rocks and soil directly, drill a little way down, and sniff gases in the air. From these tools, we learn how the red dust formed as volcanic rock weathered, how salts and clays formed where water once stood, and how seasonal carbon dioxide frost grows and shrinks at the poles. We also learn how radiation from space reaches the ground, which matters for both chemistry and future human safety. All of this points to a planet that may once have had the right conditions for life: liquid water, energy from sunlight and volcanism, and time. Whether life started there is unknown. If it did, it might have been simple and small, the kind of life that leaves chemical traces rather than clear fossils. A river delta that formed billions of years ago is a good place to search for those traces, because mud can trap organic molecules and protect them. That is why mission planners often target ancient deltas and lake beds. If nothing is found, that is also information. It tells us about limits. It tells us where the line may have been between worlds that host life and worlds that do not. Mars's small size likely set its long-term course. It cooled early. Its shield against the solar wind weakened. Its air thinned. Yet that same small size gave us a clear window into the past. The surface did not reset itself over and over. Old craters, old lava, and old river shapes survived. Every dune field, layered plateau, and battered rim holds data we can read with the right tools and patience. The planet is not dead, but its major engines run slowly now. In the marks left across its face, the record of heat, impact, wind, and water remains. The planet may no longer be geologically active on a grand scale, but in the patterns etched into its surface, the echoes of its fiery youth still remain. If you could look down on Mars in its first billion years, parts of the view would feel familiar. Instead of only bare rock and dust, you would trace rivers winding across plains, pools gathering in low spots, and wide basins that held calm water. Mars was always smaller than Earth and usually colder, yet for a stretch of time it seems to have been wet enough for water to flow in the open air. That brief watery chapter left marks that still hold their shape. Liquid moving over rock cuts, rounds, and sorts. It builds fans of sand and mud. It lays down layers. Those basic actions wrote a clear record. The first strong hints came from spacecraft in the 1,970 seconds. Mariner and then Viking showed scenes that looked less like random erosion by wind and more like organized drainage. From orbit, scientists saw branching networks that joined into larger valleys, the way small creeks feed into rivers on Earth. Some channels ran for hundreds of kilometers, with tributaries that split and rejoined. Wind can shape dunes and scour surfaces, but it does not draw tree-like patterns that head downhill. Water does. That recognition changed the way researchers read the planet. A closer look revealed more than one kind of channel. Narrow, branching valleys suggested slow, repeated flow, perhaps from rain or melting snow. Deep, wide troughs pointed to sudden floods or the collapse of underground ice and caverns, when stored water burst out and rushed across the land. Beyond those lay huge outflow channels, paths so broad and smooth they seemed to have formed in short, violent events that carried water and rocks at high speed. Along many valley mouths, Fans spread into wedges where a river slowed and dropped its load. These are deltas. They form where a moving stream meets standing water. The shape is a natural sign of a lake or a sea. One famous example sits inside Jezero crater. From orbit, the delta's outline is clear, a broad fan cut by channels and ridges. That clean geometry is why Jezero was chosen for a rover. A delta is good at preserving what washes into it. Mud and fine grains settle there. Organic molecules, if any were present, can be shielded from radiation and chemical breakdown. A rover can drive across those layers and sample different ages of the same environment, the way you can read time in a stack of pages. If life ever took hold on Mars, even at a microbial level, a place like this would be a strong candidate to keep its traces. Minerals add a second line of evidence. Some minerals on Earth only form where water is present for long enough to interact with rock. Clays are a good example. They grow when water seeps through volcanic material and rearranges its atoms into new structures. Sulfates can appear when salty water evaporates and leaves hardened crusts. From orbit, spectrometers split reflected sunlight into bands and look for the signatures of these compounds. On Mars, clays are common in very old terrains. Later layers show more sulfates. That pattern fits a climate that began with water that was more neutral and stable, then shifted toward water that was more acidic and short-lived as the planet cooled and dried. It is like finding a chemical diary. Early entries talk about long contact with liquid. Later entries talk about brines and evaporation. Comparing early Mars to early Earth helps make sense of the paths each world followed. Both were hit by impacts, both were heated from within by radioactive elements, both had volcanoes. The difference is size and distance from the Sunday Earth's greater mass let it hold a thicker atmosphere for longer, and its position gave it more sunlight. Those two factors helped keep oceans stable. Mars formed in a leaner part of the solar nebula, so it grew smaller. Smaller bodies lose heat faster, their interiors quiet down earlier, and their magnetic shields fade sooner. An early Mars with lakes, rivers, and perhaps even a shallow northern ocean would have been living on borrowed time. Still, borrowed time can be long enough for chemistry to advance. On Earth, the first strong hints of life show up by about 3.5 billion years ago, and some studies argue for earlier signs. If Mars kept surface water for hundreds of millions of years, questions about life there are reasonable to ask. How steady was that water? One view is that lakes and rivers came and went. Volcanoes can load the air with greenhouse gases and ash, warming the ground. Impacts can melt ice and release bursts of flow. Changes in Mars's tilt can change sunlight patterns and move ice around. Each of these could have created wet periods in a generally cold climate. Another view is that early Mars had thicker air and warmer temperatures for a longer span, allowing long-lived lakes and seas. The truth may include parts of both. Long phases with liquid water, interrupted by dry spells, and then a shift toward the persistent cold that we see today. Surface water, when it faded, did not simply vanish. Much of it likely moved underground or froze. In the polar caps, layers of water ice and carbon dioxide ice grow and shrink with the seasons. At mid-latitudes, soils tested by landers contain ice just below the surface. Radar from orbit has mapped buried ice deposits in many places. There are even claims of liquid water under polar ice, kept from freezing by salts and pressure. These reports are debated, but they fit the idea that Mars still holds a large part of its ancient water, only in harder to reach forms. If modern subsurface brines exist, They would be the last active echo of a much wetter past. One striking fact about Mars is how well it stores its history. Earth's surface is restless. Tectonic plates dive and rise, mountains build and wear down, rivers change course. On Mars, the crust is thick and still. Without plates to recycle rock, old features remain. A valley carved billions of years ago can sit in place with only minor softening. A delta can keep its steps and lobes. An old shoreline, if that is what some long ridges are, can follow the same curve for thousands of kilometers. The planet behaves like a slow archive. Page after page of geology remains bound together. Stand in your mind beside an ancient Martian river. You would see a channel with curved banks, small islands of gravel, side valleys merging in. Follow it outward, and you might reach the edge of a lake where the river fanned out into a broad wedge. At the edges, thin layers of lighter and darker rock stack like lines in a notebook. The colors come from different grains and from minerals formed as water interacted with the sediments. On Earth, such places are rich with chemical traces of the past. On Mars, they carry the same promise. What makes Mars different is the silence. The forms are clear. The water is gone. Reading the land there is like reading a musical score with the instruments missing. All of this leads to the idea of an ocean in the north. The northern plains, the low, smooth half of the planet, sit lower than the battered highlands of the south by several kilometers. That step between high and low regions is called the crustal dichotomy. A simple, powerful question follows. If a planet has a giant basin connected to a network of valleys, could that basin have held an ocean? Elevation maps from orbit make the possibility look reasonable. The basin is large enough to cover about a third of the planet's surface. Its edges are spread out but coherent. If water filled it, shorelines would be expected along certain contours, and some ridges and terraces do trace long, looping paths that resemble coasts cut by waves. Interpreting those lines is not easy. On Earth, tides, storms, and changing sea levels reshape coasts over and over. On Mars, any shoreline would be frozen in place by slow erosion and by the later shifts of the ground beneath it. Some scientists argue that the curving ridges are really lava flows, or that parts of the crust rose and fell after they formed, distorting what used to be smooth beaches. Others counter that, when you correct for likely uplifts and subsidence, the lines become more level, as you would expect for coastlines. The debate stays active because the answer matters. An ocean would mean a huge reservoir of water and a long-lived environment for chemistry. A different process would still be interesting, but the scale of habitability would change. If a northern ocean did exist, it would have gathered water from the south through the big outflow channels. Those channels look like the aftermath of floods that cut across barriers and dumped into the lowlands. In such a setup, rivers feed the basin, deltas grow at the edges, and sediments spread across the floor. Over time, as the atmosphere thinned and temperatures dropped, the ocean would shrink. Waves would die down, ice would spread, the shoreline would retreat, parts of the sea floor would freeze and crack. Some water would retreat into the ground or to the poles. Some would escape to space. To understand why Mars could not keep its ocean, we have to follow the fate of its air. Early on, Mars probably had a thick atmosphere. Thick air holds heat and raises surface pressure. Pressure matters because at very low pressure, liquid water is unstable. It tends to boil away or freeze. A dense atmosphere also blocks radiation and smooths out daily temperature swings. As Mars cooled inside and its core lost motion, the global magnetic field faded. A magnetic field deflects much of the solar wind around a planet. Without that shield, charged particles from the sun plow into the upper atmosphere and knock atoms loose. This escape is slow in the moment but large over time. Hydrogen is light and the first to go. Helium escapes easily as well. Heavier gases, like carbon dioxide, can be lost through other processes, including when solar storms energize the upper atmosphere. Clues to how much water has been lost lie in the air that remains. Hydrogen comes in two main forms: ordinary hydrogen and a heavier version called deuterium. When water breaks apart in the upper atmosphere, hydrogen can escape into space more easily than deuterium because it is lighter. Over billions of years, the ratio of deuterium to hydrogen in the air becomes higher if large amounts of water are lost. Measurements of this ratio on Mars show that it is elevated compared to Earth's oceans, which supports the idea that Mars once had much more water than it does now. It is not a precise gauge, but it is a strong hint that matches the mineral and geomorphic evidence. Even if the ocean was not one long era of standing water, cycles of filling and freezing could have repeated more than once. Volcanic eruptions release carbon dioxide and water vapor. They darken the surface with ash, which absorbs sunlight. Both effects can warm the air temporarily. Changes in tilt can move ice and change how much sunlight falls on different latitudes. Periods with thicker air and warmer ground could allow wide seas to return for a while, then fade again. That stop-and-start ocean is different from Earth's deep, stable basins, but it still offers large areas for water-rock interaction and for the buildup of sediments. When we picture those seas, it is important to keep the scale and the limits in mind. The water would have been salty, likely rich in dissolved minerals from volcanic rocks. The skies would have been thin by Earth standards, but possibly dense enough to move gentle waves and haze. Winter would have put ice on the surface. Spring and summer would have melted margins and opened channels from the south along the edges. Shallow bays would be places where chemical gradients formed exactly the kind of gradients that, on Earth, support rich microbial life. Whether Mars used that chance remains unknown. The record is hard to reach. The places we want to sample are far, and the signals we seek are subtle. Today, the northern plains are quiet. Standing there, you would feel only a light wind. Dust would lift and settle. The ground would be cold and dry. If you walked along one of the raised ridges that some interpret as beaches, there would be no shells, no driftwood, no sound of waves. On Earth, old seas often leave layered sediments full of fossils and chemical markers. On Mars, any such record would be in mineral forms: salts, clays, and layered deposits. Orbiters map where these occur. Rovers can drill a short distance and store samples for later return. Bit by bit, a picture forms. But the ocean, if it existed, is now only shapes and chemistry. All paths lead back to the atmosphere. The blanket of gases over a planet controls pressure, temperature swings, and the behavior of liquid water. In its earliest times, Mars seems to have worn a thicker blanket. Over time, that covering thinned. The causes are linked to the planet's size and cooling rate. Early Mars probably had a molten metal core, moving and generating a magnetic field. That field is an invisible structure that guides charged particles around a planet. Earth's field deflects most of the solar wind and helps keep our air in place. Mars's field did not last. As the core cooled and partly solidified, the dynamo slowed and failed. The shield weakened and then collapsed. With no global field, the solar wind could reach the upper atmosphere directly. Once that happened, the escape of air stepped up. The sun sends out a steady stream of charged particles, and it sometimes erupts, sending even stronger bursts. When that flow hits the thin, heated gases high above Mars, it transfers energy. Atoms and molecules in that region can gain enough speed to leave. The lightest species go first. Hydrogen, whether from water vapor or other sources, is lost quickly. Helium, produced by radioactive decay and delivered by the solar wind, also drifts away. Carbon dioxide, the main remaining gas, can be stripped during storms and through processes driven by sunlight. Bit by bit, the atmosphere shrank. With less air, the ground lost heat more easily. With lower pressure, water at the surface became unstable. The hydrologic cycle weakened. NASA's MAVEN mission has watched these processes in action since 2014. Its instruments sample the upper atmosphere, count escaping ions, and track how conditions change when the sun is quiet versus when it is active. The measurements show that escape still occurs today, slowly on human timescales but cumulatively over geologic time. They also show spikes during solar storms, when the flow from the sun strengthens and magnetic fields change shape. Those spikes are direct proof that the sun's mood matters for Mars's air. By measuring the rates and tying them to different kinds of solar activity, scientists can reconstruct how loss might have proceeded in the past when the young sun was louder and more active. MAVEN's data tighten the story of a world that cooled, lost its shield, and then lost much of its sky. It has measured how solar storms accelerate atmospheric loss even today. Even though the present loss is tiny, the total over billions of years is large enough to explain much of the missing air. A sky that may once have been thick and blue turned thin and dusty, with barely enough pressure to brush a rock. Standing under it would feel strange. Daylight would seem dimmer than on Earth, yet oddly sharp, like noon seen through a light filter. The sun would look smaller, about 2/3 the size it appears from Earth, and its glare would pass through a veil of reddish dust. The air would not feel like air at all. It is less than 1% of Earth's surface pressure, far too thin to carry a strong scent or a full breath. Without a suit, the danger is not only cold, but the lack of pressure. Your lungs could not take in enough oxygen. Wind adds to the illusion. Speeds can reach 100 kilometers an hour, but with so little mass in the air, it pushes softly. A gust that looks fierce would feel like a gentle breeze. That thinness changes what the sky looks like. Near the ground, the horizon blends into a muted, rusty tan that matches the salmon-colored soil. Close to the sun, fine dust scatters light so the sky can take on a butterscotch or pale yellow tone. At sundown, the pattern flips. Dust scatters red light away and lets more blue slip through, so sunsets can shine with a brief, cool glow. They are not dramatic like Earth's fiery displays. They are short and soft, a blue halo fading over a quiet plain. With little air to store heat, warmth leaves quickly after dark. Days can be chilly even in full sun, and nights drop fast, sometimes by dozens of degrees in a few hours. Heat has nothing to hold it and radiates into space. Losing the atmosphere did more than cool the ground. It narrowed what the planet could support. Thick air shields a surface from radiation and helps liquid water stay stable. As the air thinned, radiation from the sun and deep space reached the ground more easily. Levels rose to amounts that most known life would find hard to endure at the surface. Any living things would have needed to retreat below ground, into rock and soil, or they would have vanished. Even so, the sky still holds a quiet beauty. Dust paints smooth gradients at dawn and dusk, Thin clouds made of water ice or carbon dioxide drift high and slow, catching pale light and throwing faint shadows. There is no rustle of leaves and no insect hum. The stillness makes the sky feel both wide and close. Each lost atom is part of a long record, a slow change written into the color of the horizon, the sharpness of stars at night, and the hiss of wind too light to carry a voice. The thin sky is not empty. It is a visible remnant of a climate that once had more comfort, a faint sign of a shield that failed, and the fragile roof over a world that keeps its past in view. Mars holds a great deal of dust. Not household dust, but a fine, iron-rich powder spread across plains, hills, and craters. It clings to almost everything it touches and gives the planet its red color. That red is mostly a coating, not the native color of all rocks. Iron in the crust reacts slowly with trace oxygen in the thin air and with oxidants made by sunlight. Over long spans, grains pick up a film of iron oxide, the same compound that tints some Earth deserts and coats old steel with rust. Temperature swings and wind grind rock into ever smaller fragments until the average grain is tiny, finer than talcum powder. Because the particles are so small, they behave almost like smoke. Even a modest gust can lift them and keep them aloft for long distances. Over time, this constant lifting and settling creates a steady haze near the lower atmosphere. From the ground, that haze softens light and makes the characteristic butterscotch skies. From orbit, it mutes landscapes into rust and ochre. Dust does not lie evenly. Sun-warmed surfaces can drive narrow whirlwinds called dust devils. On Mars, some grow higher than a kilometer, winding across plains and leaving dark streaks that mark where they clean the surface. They spin because hot air rises, and the thin atmosphere lets that motion organize into columns. Despite their height, they are gentle by Earth standards. You could stand inside one and not be thrown, but they are very good at lifting grains and feeding the haze. Beyond these local whirls are the large, slow systems that sometimes grow into planet-wide storms. Every few years, the right pattern of sunlight, winds, and surface heat starts a feedback cycle. Dust lifted from one region warms the air, which changes winds, which lifts more dust. Within weeks, the haze can spread around the globe. From space, the planet looks like a pale orange sphere with only faint hints of its dark markings. These storms can last for months. The winds in such storms move fast, but they carry little force because the air is thin. The main hazard is the dust itself. It blocks sunlight. For vehicles that depend on solar power, that can be fatal. In 2018, a global storm dimmed the lights so much that the Opportunity rover could no longer charge its batteries. Without power to keep heaters on, the cold seeped in, and the mission ended after nearly 15 years of work. Dust also changes the climate in slower ways. In the air, grains absorb and scatter sunlight. The atmosphere warms while the surface under it cools. That shift changes temperature gradients, tweaks wind patterns, and may influence the behavior of polar ice. Some researchers suggest that dust has helped lock Mars into its current cold, dry state by altering how heat moves between ground and sky. For explorers, dust is a constant engineering problem. Fine grains creep into joints, gears, and hinges, wearing down parts. They stick to glass and filters, dulling camera images. They coat solar panels, cutting power. Designers add brushes, wipers, and vibration to shake dust loose. But no method is perfect. The longer a mission lasts, the more dust builds up, Future crews will have to manage it too. Lunar dust brought back by Apollo was sharp and clingy, and Martian dust is likely similar. Inhaling it would pose health risks, and the electrostatic charge helps it stick to suits and tools. It could be tracked into habitats, unless strict procedures and airlocks capture it. The same iron oxide that makes the world striking from orbit can be a stubborn problem on the ground. Dust also shapes the scenery. In some places, wind-blown dunes ripple like waves that never move, their dark basaltic sands set off against pale dust in the hollows. In others, dust lines the sheltered side of rocks, tracing the wind's path with soft shadows. The grains are a record, as well as a nuisance. Each sample holds fragments from around the planet, mixed by winds over long spans. Studying dust can reveal the chemistry of far-off regions without traveling there. As if Mars had passed around samples for ages, it may also carry clues about past habitability. If microbes ever lived on Mars, traces of their chemistry could have been trapped in fine layers or grains that formed in water. The odds of finding such signals are uncertain, but the dust is a fair target because it archives surface processes and, perhaps, faint signatures of biology. From local devils to global veils, dust is always present. It smooths sharp edges, softens colors, and sometimes erases contrasts until the planet looks like a single tone. Yet it also preserves. Every rover track, every gust, is part of a cycle that began when the first rocks started to crack. On this world, even tiny particles matter. The color of the sky, the reach of a mission, and the outline of a dune can all depend on grains so small you could hold millions in one hand. Dust is not just part of the landscape. On Mars, it often is the landscape, ever shifting and patient, waiting for the next wind to lift it again. Set this fine veil aside and look west across the planet, and you come to mountains that rewrite the idea of tall. Earth's highest peak rises a bit over 8.5 kilometers above sea level. On Mars, that would seem modest. Olympus Mons towers about 22 kilometers from base to summit, nearly 3 times Everest's height, and spreads so wide that the curve of the planet hides its far side. It is a shield volcano, a broad mound built by many, many lava flows that spread in gentle layers. The lavas on Mars are relatively fluid and can travel long distances before cooling. With no moving plates to drag the crust over hot spots, the same vent can keep feeding one structure for millions of years. On Earth, plate motion builds chains like Hawaii. On Mars, a fixed crust let one volcano grow into the largest in the solar system. East of Olympus Mons lies the Tharsis region, a vast volcanic rise dotted with other giant shields. Ascraeus Mons, Pavonis Mons, and Arsia Mons stand in a line along the uplift. Each would be a headline mountain on Earth. Here, they share the stage with an even larger neighbor. The whole bulge is so massive that it has influenced the planet's shape and stress patterns. The weight of Tharsis may be tied to fractures and valleys elsewhere, including the enormous canyon system called Valles Marineris. The scale of these volcanoes tells us that Mars once had a strong internal heat flow. Molten rock rose through weak zones and spilled across plains and flows that could stretch for hundreds of kilometers. Some eruptions likely lasted weeks or months, adding gas and ash to the air. If surface or underground ice was nearby, heat could have melted it and sent floods racing down slope, cutting channels and changing the land quickly. Despite their size, the great volcanoes are quiet now. Evidence suggests that some eruptions on Mars might have happened as recently as a few million years ago, which is very recent in geologic terms. But Olympus Mons, and its neighbors have not been active in any record we hold. With much of the interior heat lost and no plate tectonics to generate constant stress, the mantle has slowed. It no longer feeds the colossal constructions it once raised. The silence is striking. If you stood near the base of Olympus Mons and looked up, the slope would seem mild, more hill than cliff. That is because the mountain is spread out. The grade is gentle, but it continues for hundreds of kilometers. In low gravity, the climb would be easier per step, yet the distance would be deceiving. The horizon would keep sliding away. The summit caldera, a group of collapsed craters where the roof fell after magma withdrew, is immense. Edged by cliffs and cut by cracks, it records the power that moved beneath and the empty spaces that followed. Other volcanic forms are scattered across the planet. Broad lava plains cover huge areas, dotted with small shields that never reached the scale of Tharsis. There are cones made by explosive eruptions of ash and cinders, steep-sided and sharp in the thin air. Some regions bear the mark of fissure eruptions, where lava poured from long cracks instead of a single vent, leaving dark, sinuous flows that show up clearly from orbit. All of this is more than a gallery of ancient fire. It is a guide to the planet's interior, its cooling history, and its past surface environments. Volcanoes release gases such as water vapor and carbon dioxide. In early times, those gases helped thicken the atmosphere and warm the surface. Heat from active regions could have created warm niches under ice, possibly providing refuge for simple life. The connection between volcanism, air, water, and habitability weaves through Mars's story. Today, the volcanoes endure as tall, steady monuments. They will not crumble quickly. The air is too thin for strong rainfall, and liquid water is rare at the surface. Erosion works slowly. Unless struck by large impacts or buried by new lava, Olympus Mons will likely look similar many millions of years from now. It is a mountain that outlasted the engines that built it, where Earth's biggest peaks rise from moving plates and change as climate and ice sculpt them. These Martian giants stand mostly unaltered, lit by a smaller sun under a high, sparse sky. The stillness carries a certain weight. On Earth, eruptions remind us the planet is active. On Mars, these immense shapes remind us of a world that once flowed with fire and now rests. The slopes that reach towards space are set in time. Dust drifts over them, tracing faint lines on rock that has not felt deep heat in ages. Standing there, the feeling is not of risk, but of scale and duration. Every stone would be part of a long record of rising and cooling. Every horizon would arc across a mountain unlike any on Earth. Time moves differently here. Millions of years pass quietly, and the marks of ancient eruptions still structure the land, even in the long pause that follows. Valles Marineris on Mars pushes the idea of a canyon far beyond anything on Earth. It runs for more than 4,000 kilometers, with sections over 200 kilometers wide and drops that reach 7 kilometers deep. If a feature like this crossed our planet, it would stretch almost from the Atlantic to the Pacific, cutting straight through mountain ranges on its way. From orbit, it looks like a vast system of gases. It dominates the equatorial face of Mars and is one of the clearest signs that the planet's crust was once under stress. Its name comes from the Mariner 9 spacecraft, which mapped Mars in the early 1970 seconds and revealed this immense structure. The canyon is not a single trench. It is a chain of linked chasms, basins, and corridors with stepped walls, terraces, talus fans, and layers stacked like a library. When seen from above, the system resembles long parallel fractures that widened and deepened over huge spans of time. On Earth, large canyons are often carved by rivers or ice. Mars likely did not run surface water long enough to cut something this large by flow alone. Most scientists think the story begins with the crust stretching and breaking. The rise of the Tharsis volcanic region to the west may have lifted and pulled the crust until major faults opened. Once those fractures existed, gravity took over. Walls collapsed in landslides. Underground voids fell in. Heat and pressure likely sent floods of water or lava through some sections, scouring and enlarging the chasms. There are signs that water took part at times. In some branches, channels lead into basins where sediments collected, and there are layered deposits that look like lake beds. Such lakes would not have lasted forever. Warmer intervals triggered by volcanism or shifts in climate could have allowed water to pool for a while before freezing, evaporating, or draining away. What remains is a careful record. The canyon walls preserve layers from many eras. Volcanic ash, blown in from distant eruptions, river or lake sediments laid during brief wet phases, and wind-built sheets from long dry spells. Landslides have cut windows through these stacks, exposing vertical profiles kilometers high. From the floor, those cliffs would rise in tiered walls that catch light in pale yellows, reds, and browns. In the thin air, color contrasts soften with distance, while the geometry stays sharp. Scale is hard to grasp without motion. Imagine flying low along the floor, passing through sections that open into wide basins and then tighten into narrow corridors where the walls press close. Side canyons enter like tributaries on either side. In the weak Martian atmosphere, light scatters through dust and gives the shadows soft edges, even at noon. The canyon is deep enough that air pressure at the bottom is higher than on the adjacent plains, and temperatures can be a little milder. Winds flow along the length like rivers of air, gathering dust and moving at great distances. In places, the floor is littered with the remains of giant landslides. Here, low gravity lets debris spread in broad tongues that look almost like thick slurry that came to a stop. These slides rank among the largest known anywhere, and they underline how relief, gravity, and dry materials interact differently on Mars than on Earth. The sky, when viewed from the canyon floor, would be a narrow strip. Morning light would descend the walls in stages, touching ledges and terraces before reaching the floor. Evening light would climb in reverse, leaving the lower levels in blue-gray shade while the rim glowed. For explorers, a place like this holds both risk and value. The relief complicates access. The descent from rim to floor could take hours or days by a safe route, and climbing back out would be harder still. Yet the exposed layers would be a major scientific advantage. Each layer is a time marker, with minerals that record the environment when it formed. A mission that moved from one bench to the next could read climate shifts written in color, grain size, chemistry, and texture. The canyon shelter from wind and radiation also makes it a candidate for long-term study sites. Some scientists think the walls may hide caves formed by lava tubes or by water cutting into weaker layers. Caves would offer protection from radiation and thermal extremes, and could be good places to seek preserved organic compounds if they exist. All of this is useful, but the canyon's simple presence also speaks to the power of the planet's interior past. To crack the crust across such a long belt requires large forces. To hold the walls for billions of years requires slow erosion. Valles Marineris is both a scar from stretching and a museum of rock types and climates. It narrows our guesses about how Mars cooled, how its crust thickened, and how water and wind alternated as the main sculptors of the surface. At the far ends of Mars, the poles gleam against the red terrain. Two caps, one in the north, one in the south, stand out with bright spirals and swirls. They are not thin frost alone, but deep stacks of ice and dust. The northern cap, Planum Boreum, spreads wider. The southern cap, Planum Australe, is smaller in area but thicker. Each sits atop layered deposits that work like tree rings. Layer upon layer records winters, summers, dusty seasons, and clear seasons, tracking the planet's long-term tilt changes and climate swings. Mars's poles are not quiet in the way Earth's ice sheets are. Much of what looks white in many images is dry ice, frozen carbon dioxide. Each Martian year, winter grows cold enough that carbon dioxide from the atmosphere freezes out onto the winter pole, adding a seasonal layer that can be up to a meter thick. At the same time, the opposite pole is in summer, and its seasonal dry ice turns directly from solid to gas, raising the air pressure. The global atmosphere breathes with this cycle. Total surface pressure drops during winter at one pole and rises during its summer when the frozen carbon dioxide returns to the air. This exchange moves a large fraction of the atmosphere from sky to ground and back again, year after year. The spring changes are dynamic. Sunlight creeps back, and the dry ice often sublimates from the bottom because sunlight can pass through the translucent slab and heat the ground beneath. Gas traps under the surface, pressure builds, and then vents open. Jets rush out and carry dust that stains the ice and fans that point with the wind. Seen from orbit, these dark fans look like ink brush marks and form new patterns each spring. The process is not violent the way geysers are on Earth, but it is active and steady, a strange behavior from a world where the air itself regularly freezes. Below the seasonal dry ice lies the more permanent water ice. If you could melt all the water stored in the polar caps, the resulting ocean would cover the planet to an average depth of more than 10 meters. That water is important for science and for future operations. It holds climate records in its layers. It could also supply crews with drinking water, be split into oxygen and hydrogen for breathing and fuel, and be used for shielding against radiation. The layered deposits show fine banding that reflects how Mars's tilt, its obliquity, has shifted over long cycles. When the tilt is higher, the poles receive more sunlight and can lose ice to the atmosphere. Water migrates toward lower latitudes and may even build frost or ice deposits far from the poles. When the tilt is lower, the poles are colder and more water stays locked into the caps. Reading these layers lets scientists reconstruct a climate timeline that spans millions of years. On the ground, the poles feel otherworldly, even compared to the rest of Mars. The horizon is low and bright. The wind is thin and cold. Frost coats rock and dust, sometimes so lightly that it looks like a glittering film before the sun clears it. In winter, the sun does not rise for months, and temperatures plunge below 100 degrees Celsius. In summer, the sun circles low around the horizon and never sets, throwing long shadows that sweep across grooved and pitted ice. Spiral troughs carve deep into the caps, likely guided by winds that follow the topography. The patterns they make are striking and repeat across scales, wide curves from orbit and smaller curves along their walls. The whole scene changes seasonally, yet the deeper layers remain as a stable archive. These caps are not only pretty to view from above, they are central to how Mars works now. They modulate air pressure, capture and release carbon dioxide, and store vast amounts of water. They also record past conditions that help explain when and where ice and perhaps liquid water might have been more common at lower latitudes. If the planet ever had widespread habitable environments, the polar layers might help set their timing and pace by showing when the air was thickest and when temperatures favored melting. Far above the surface, two small moons trace quiet paths through the sky. Phobos and Deimos are not like Earth's moon. They are small, irregular, and dark, more like captured rocks than polished spheres. Phobos, the larger, is only about 22 kilometers across at its widest. Deimos measures roughly 12 kilometers. Their low gravity is too weak to pull them into a round shape. They are pitted by craters, lined by grooves, and covered with loose material that shifts slowly over time. To the eye from Mars, Deimos behaves most like a very bright star that rises and sets. It is small and distant enough that it shows very little disk without magnification. Phobos is closer and moves fast. Because it orbits below the height where a satellite would stay above one spot, it races west to east across the sky, rising in the west and setting in the east. It completes a trip around Mars in a little over 7 hours, so you can watch it cross the sky several times in one Martian day. Its speed makes its passages striking at dawn and dusk. Where these moons came from remains open to study. One idea is that Mars captured 2 asteroids long ago. Their irregular shapes and dark, carbon-rich surfaces resemble a class of asteroids known as carbonaceous objects. Capturing such bodies into stable orbits is not simple. It likely requires energy loss, perhaps through interaction with a thicker atmosphere in the past, or with debris or a series of gravitational encounters that bled away speed. Another idea is that a large impact struck Mars and sent debris into orbit. That material then clumped into small moons. This model can explain some orbital details but raises questions about composition if the moons look asteroid-like. It is possible that both ideas contribute. Debris could mix with a captured object, or multiple events could shape what we see now. Their futures are different. Deimos, farther out, is slowly drifting away from Mars. Over great spans, it may leave the planet's grasp and become another small body orbiting the Sunday. Phobos, by contrast, is on a slow inward spiral. It orbits only about 6,000 kilometers above the ground, so tidal forces between Mars and Phobos are drawing it down by a couple of meters per century. That is slow in human terms, but decisive in geologic terms. In tens of millions of years, it will either crash into Mars or be pulled apart by tidal stress into a ring. The second outcome may be more likely because Phobos shows long grooves and fractures that could be signs of internal weakness. If it breaks, Mars would carry a short-lived ring system, bright at first, and then thinning over time as fragments fall or drift away. For future exploration, the moons are practical as well as poetic. Phobos' low gravity makes landing and takeoff easy, and its constant motion above Mars could support relay antennas and instruments looking down. Deimos is even gentler to leave and could serve as a quiet staging point for missions that head outward. Working on either would require careful anchoring. Gravity is so weak that a strong shove could send a person or a robot drifting, but the advantages are clear. From their surfaces, Mars would hang like a large globe in the black deserts and volcanoes visible through the thin haze. The view itself would be useful, allowing mapping and monitoring of dust storms, clouds, and surface changes. Seen from the ground, Phobos steals scenes. It can pass in front of the sun and cast a racing shadow, creating fleeting partial eclipses. The dimming lasts only tens of seconds because the moon moves so quickly, but the effect is clear, a fast, soft-edged shadow that sweeps across the landscape. Deimos's eclipses are faint and easily missed without instruments. At night, the moons behave like a slow dancer and a sprinter. Deimos glides. Phobos hustles. They repeat their paths with a rhythm that becomes familiar if you watch for a few nights. Their orbits and fates add a moving piece to the steady face of Mars. Phobos is the restless one, pulled inward, likely to shatter or fall. Deimos is the drifter, easing outward over time. Their existence still holds clues about the past, about impacts, captures, and debris, and about the nature of small, weakly bound bodies. They remind us that a world can carry companions that do not look like scaled-down versions of bigger moons. The pair is rough, small, and quiet, yet they matter for both science and operations. They offer platforms, samples of primitive material, and lessons in low-gravity behavior. They also shape how the sky feels. On a planet with a thin atmosphere and long, quiet nights, the quick crossing of Phobos and the slow rise of Deimos add motion and measure to the dark. Their presence would be a reminder that even the smallest companions can shape the way we see a world. Mars is famous for its red color, deep, rusty, and easy to recognize from a single glance. That look is so common that almost every language calls it the red planet. Yet the rocks themselves are not all naturally red. The color mostly comes from a fine coating that lies on top of almost everything, dust-rich in iron oxide. The chemistry is straightforward. Many Martian rocks contain iron, as Earth rocks do. Over billions of years, wind-blown sand, tiny impacts, and daily temperature swings broke those rocks into powder. In the thin air, small amounts of oxygen and other oxidants reacted with the iron, turning it into iron oxide rust. The coating is only microns thick, but it is spread almost everywhere, and the combined effect gives the whole world its burnt orange glow. From space, the result is striking. Against the black of space, Mars can look like a glowing ember. Up close, the palette is more varied. Rusty tones still dominate, but they are not uniform. Where winds have swept the dust aside, darker, volcanic rock shows through. These patches can appear charcoal gray to black, especially where basalt, the common volcanic rock on Mars, sits near the surface. In other places, dust mixes with lighter minerals and softens the red into peach or tan. Minerals add still more range. Certain clays and salts can reflect light in greenish, gray, or bluish tints under midday sunday. Sulfate deposits, which form where salty waters once evaporated, can look pale yellow or nearly white. Some crater walls and fresh impact sites even show streaks of brilliant white, likely water ice or seasonal frost holding on in shade. The polar caps look crisp white in winter, then take on pink tones in summer as dust settles across their surface. Volcanic provinces contribute their own contrasts. The broad lava plains around Olympus Mons and the other Tharsis volcanoes often look darker because their basalt is less weathered. Over time, dust will spread over these flows and mute them. But for now, the sharp edges and dark sheets remind us that Mars holds both ancient and relatively fresh landscapes. Seasons also paint the world. During the global dust storms that sometimes wrap the planet, the air fills with fine particles. The sky turns soft orange, shadows weaken, and the ground's contrast flattens. When the storms end, the dust settles in new patterns, refreshing color boundaries across dunes, plains, and crater floors. The sky itself behaves differently than Earth's. Most days, it is not blue. It is a warm butterscotch color. Fine red dust suspended in the thin air scatters sunlight in a way that lets warmer tones through while pushing blue light out of most of the sky. Near sunset, that effect reverses. The region around the sun can turn a soft, cool blue, while the horizon glows in reds and oranges, almost the opposite of Earth. The blue period is brief, lasting minutes, then fading to the sharp darkness of space. If Mars had a thicker, cleaner atmosphere, Rayleigh scattering would dominate like it does on Earth, and the daytime sky would likely appear blue. Under that light, the red ground would pop more strongly, and shadows would soften. In deep past, when the air may have been thicker and wetter, the planet's colors might have been muted by clouds and haze. Stretches of water would have added dark blues and greens, while damp rock would have darkened the nearby land. Today, the dryness determines the palette. Dust does not wash away in rain, and snow does not blanket it for long. It moves with the wind, settles, and lifts again. Rover tracks start dark, then fade as dust drifts back. Fresh craters look light or dark, depending on whether they expose bright ice or dark rock, and on how quickly dust recoats the scar. The result is a slow, subtle art. Thin layers, soft edges, and changes spread over years instead of hours. The colors shift with time of day. Morning light, low and cool, can make the land glow in copper tones, while long shadows draw clear lines across ripples and rocks. Midday washes the surface toward paler hues, and evening deepens the reds again as the sun approaches the horizon. Just before night, a brief bloom of blue forms around the setting Sunday. Then the stars come out sharp and steady. Mars is called the red planet for a reason, but it is more than one color. It is a scene painted by chemistry, climate, and time, where rust shares space with gray basalt, pale salts, and white frost. Look closely, and variety appears everywhere. For a long time, Mars was a world we knew only through images, quiet panoramas of rock, sand, and sky. In 2021, microphones aboard NASA's Perseverance rover added something new: sound. For the first time, we could listen to Mars instead of only looking at it. The first lesson was simple. Mars is very quiet. On Earth, even in calm places, there is a background hum leaves, water, insects, distant engines. Mars has no trees, no flowing streams, and no busy wildlife. The baseline is a deep, steady silence. When a sound does happen, it stands out cleanly. The wind is one of the most common sounds. It does not roar like in movies. It whispers. Recordings capture a soft hiss with gentle rises and falls as gusts pass over the rover's mast. Sometimes a stronger gust adds a brief whoosh, but even then the thin air keeps the volume low. Mechanical sounds from the rover are also audible. The creak of wheels, the crunch of grains under the treads, faint clicks as instruments adjust and sample. These noises are clear examples of how sound behaves in a different atmosphere. Martian air is less than 1% as dense as Earth's and is made mostly of carbon dioxide. That combination slows sound and damps high pitches. A voice spoken in open air would sound softer and lower, and it would take a bit longer to reach your ear. Because different frequencies travel at slightly different speeds in CO2 at low pressure, high and low parts of a sound can separate a little as they move an effect we do not notice naturally on Earth. Sound also fades quickly with distance. A noise that is obvious at a few meters might vanish after a short walk away. Echoes in canyons or craters would be faint and odd. Perseverance carries a laser tool called SuperCam that studies rocks. Each laser pulse makes a tiny snap when it vaporizes a pinpoint of material. In recordings, these snaps sound like distant static. Scientists use the spacing and loudness of those clicks to learn about hardness and composition. Dust devils, small, spinning columns of air and dust, have also passed near the rover. When one crosses, microphones pick up a fluttering rush as grains tap the rover's body. It sounds a bit like very light rain on a tent, but with a dry texture. These brief events mark some of the rare, lively moments in an otherwise hushed world. Even the air itself adds a near-inaudible background hiss, the sound of countless molecules moving. Sensitive instruments can detect it. To human ears, it would be barely there. Standing on Mars, the quiet would feel almost physical. Your own footsteps would be loud to you at first, then swallowed by space. A breeze would whisper in your helmet rather than push on your body. From time to time, you might hear the soft tick of a grain of sand striking rock. In a way, Mars is not truly silent. It is selective. It allows a few sounds and gives them space. There is no crowd of noises competing to fill every moment. The recorded soundscape matches the rest of the planet, spare, clear, and informative if you listen carefully. For as long as people have watched Mars, one question has stayed close. Is it alive in any form? Not forests and animals, but microbes, small life that can thrive in quiet places. For centuries, the idea was guesswork. In 1976, the Viking 1 and Viking 2 landers ran the first direct biology tests on another planet. Each lander carried experiments to look for metabolism, the chemical signs of life at work. One test added nutrient solution tagged with radioactive carbon to a soil sample. If microbes ate the nutrients, they would release radioactive carbon dioxide that the instruments could measure. Another test heated soil to see if gases released had patterns linked to biology. The results did not line up neatly. One experiment returned a signal that looked like something breathing. Other tests did not match that behavior. The chemistry seemed unusual, and over time, most scientists concluded that the reactions came from the soil itself rather than from living cells. Mars's surface chemistry is harsh. Ultraviolet sunlight and oxidizing compounds break down organics. The Viking results taught caution. Was that signal life, or was it reactive soil in an unfamiliar environment? The debate has never fully ended, but it set the tone for later missions. Newer missions have asked a different first question. Was it ever habitable? That means looking for past liquid water, organic molecules, and environments where life could have survived. Over time, evidence has accumulated that ancient Mars had many such places: river deltas, lake beds, groundwater systems, and hydrothermal zones near volcanoes and impacts. A striking modern clue is methane. On Earth, many microbes make methane, though rocks can produce it without life through water-rock reactions. In Mars's thin air, methane is destroyed by sunlight and chemistry in a few hundred years or less. If methane is present today, something is adding it. Orbiters and rovers have reported methane at very low levels, with Curiosity measuring small seasonal changes, slightly more in summer, slightly less in winter. Some remote reports have found plumes. Other instruments have not seen them at the same time. The mix of detections and non-detections is frustrating. Methane keeps the question open but does not answer it. It could seep from underground pockets, be made by reactions in the crust, or be produced by microbes in the subsurface. Mars makes it hard for life to leave clear traces on the surface. Radiation breaks down complex molecules. Reactive dust and salts can erase delicate structures. If life existed long ago, the best preserved signs may lie a few meters underground, where rock and soil shield against radiation and where salty brines could sometimes form. Drilling that deep is beyond current rovers. Still, the surface holds promising rocks. Ancient deltas and lake beds are good at trapping and preserving organic matter on Earth. That is why Perseverance is collecting cores in Jezeros's delta. Those samples are sealed for a future return to Earth, where laboratories can analyze them with tools far beyond what a rover can carry. Europe's Rosalind Franklin rover, planned to carry a deep drill, is designed to reach meters into the ground to look for organics and chemical patterns that match life's work. Even with such samples, proof will be demanding. Scientists will look for multiple lines of evidence that fit together: shapes in rock that resemble microbial mats, organic molecules with patterns that biology favors, minerals that form in gentle waters, and isotopic ratios that hint at biological processing. None of these alone is enough. Together, they can build a case that stands. The history of the Viking results is a reminder to ask for strong evidence and to check for non-biological paths first. It is also possible that Mars had life and lost it, leaving only faint hints, or that it never crossed the threshold from chemistry to biology, even in watery places, or that it still hosts microbes deep below using chemical energy in the dark. The search aims at whispers, small gases, thin films, tiny shapes. That is not failure. It is the nature of the question. Mars is not a dead rock like our moon or a furnace like Mercury. It shows a record of water, energy, and change, the basic ingredients that, on Earth, led to life. Whether Mars made the same leap remains unknown. The answer, whenever it comes, will matter far beyond one planet. Long before the tools existed to try it, people pictured walking on Mars. Early writers filled pages with dome-covered towns, canals under dusty skies, and a horizon that felt both close and strange. Telescopes showed only a blurry face, so imagination did the heavy lifting. Those stories were part fantasy, part early science, and they planted a seed that kept growing as our knowledge sharpened. As measurements replaced guesswork, the drawings of fictional cities slowly gave way to serious sketches of real missions. By the mid-20th century, engineers were calculating fuel, mass, and flight paths. Visionaries like Wernher von Braun outlined fleets of ships, crew rotations, and surface stays measured in months. The biggest hurdle in those early plans was simple and brutal: the trip, a journey of many months through deep space, fully dependent on closed life support and careful planning with no quick return. Today, the idea is more concrete. Agencies and private companies have mapped candidate routes and landing zones. Rovers and orbiters have scouted rocks, slopes, and weather patterns. We understand the main obstacles better, and they are not small. Radiation is near the top of the list. Earth's thick air and magnetic field deflect many charged particles from the sun and from cosmic rays. Mars has little of either. On the surface, radiation levels are far higher than on the International Space Station. Over a long stay, that raises the risk of cancer, damages cells, and stresses electronics. Solutions exist but are heavy: thick shielding, habitats buried in regolith, or stations tucked into lava tubes or other natural caves. Each approach demands mass, equipment, and time. Dust is another constant factor. Martian dust is fine, iron-rich, and often charged. It sticks to surfaces and works its way into seams, joints, and filters. It holds perchlorates, reactive salts that are a concern for health and materials. It can scratch helmet visors, foul bearings, and coat solar panels. Keeping dust outside requires strict suit ports or dedicated airlocks, smart airflow, and steady maintenance. None of this is impossible, but all of it adds workload every single day. Isolation magnifies every task. A crew on Mars would be farther from home than any human group has ever been. Radio signals can take from about 4 to more than 20 minutes each way, depending on the planet's positions. There is no real-time conversation. A problem must be understood and solved by the people on site with the tools at hand. Medical issues, mechanical faults, and simple morale all sit on that same delay. The setting is also stark. The landscape is quiet and sparse. Long stretches look similar, and the color palette is narrow. Good design, regular contact, meaningful work, and private space will matter as much as power and water. Gravity sits in an uncertain middle. Mars pulls at about 38% of Earth's gravity. That will make lifting and moving equipment easier, but the long-term effects on muscles, bones, eyes, and circulation are unknown. We have data from microgravity on stations and from short returns to Earth, but not from a steady partial gravity environment. Countermeasures, exercise, smart nutrition, and possibly drugs will help. Whether they fully solve the problem is an open question, best answered by careful, step-by-step missions. Even with all this, the draw remains. Imagine that first day. A hatch opens, dust hangs in weak gravity. The sky is butterscotch. The sun is smaller and whiter than you are used to. Your steps feel light, and each stride lifts a small puff that takes its time to fall. Low hills line the horizon. The air is clear but thin and unbreathable. Temperatures bite through layers. You know that every second of comfort depends on fans, heaters, valves, and a thin shell between you and the outside. Inside the habitat, the air is near Earth norms. Every system matters. Oxygen recovery, carbon dioxide removal, water recycling. Coffee might come from melted ice or from moisture squeezed out of the air by a machine. Work begins soon after landing. Weather masts go up. Radiation monitors start logging. Solar arrays unfold. A small greenhouse inflates and seeds sprout under LEDs. Nothing about the moment is casual, and that is the point. It is a stress test of procedures and design, and it is also the first proof that people can build a routine somewhere other than Earth. Night reveals a sky punctured by bright, steady stars. Phobos crosses quickly. Deimos glides. The cold deepens. The habitat hums. You feel the distance to home not only as kilometers, but as time and attention. Rescue is not a plan. Reliability is. Standing there, the reason people push toward this place becomes plain. It is not only to touch another world, it is to show that life from Earth can set up shop beyond where it began, that our toolkit is broad enough and our practice careful enough to keep people well in an unforgiving setting. Before any boot prints, robots laid tracks and sent pictures. For decades, they have been our hands and eyes. Each mission took a piece of the puzzle and left better questions behind. Early flybys. In the 1,960 seconds, Mariner 4, 6, and 7 returned the first close images. The view was harsh, a cold, cratered surface that reminded many of the moon. One sweep of those photos killed off old ideas about straight canals. In 1971, Mariner 9 became the first craft to orbit another planet. It arrived to a world wrapped in a global dust storm. As the air cleared, the camera revealed shield volcanoes taller than any on Earth, a canyon system that cut across the equator, and networks of dry valleys. Mars was not a simple desert. It was varied and active in deep time. Next came the first landings. Viking 1 and Viking 2 reached the ground in 1976. Each carried cameras, weather gear, chemistry labs, and biology tests. The images showed rocks, sand, and sky with a clarity that still holds up. The biology results were mixed and sparked a debate that continues, but the missions proved that soft landing, remote lab work, and long surface operations could all succeed. After a pause, exploration shifted to mobile platforms. Pathfinder landed in 1997 and released Sojourner, a small rover that rolled, sniffed, and posed for photos that still charm. In 2004, twin rovers, Spirit and Opportunity, bounced down and unfolded. They were built for 90 Martian days and then kept going. Spirit fought through sand traps and climbed hills for more than 6 years. Opportunity lasted nearly 15 years and covered more than 45 kilometers, reading rocks that formed in ancient water and watching dust clear off its panels after storms. In 2012, Curiosity landed using a daring sky crane system. Powered by a nuclear source, it carried a full lab, drills, ovens, spectrometers, and cameras on a mast. It confirmed that Gale Crater once held lakes and that clays formed in calm waters. It still climbs Mount Sharp, reading layers like pages and building a timeline of environments. In 2021, Perseverance landed in Jezero Crater, a fossil river delta. It drills cores, seals them, and sets them aside for a future sample return mission. With it came Ingenuity, a small helicopter that proved powered flight in thin air. Planned for a few tests, it flew again and again, scouting paths and showing how air vehicles can work here. Above, orbiters such as Mars Odyssey, Mars Reconnaissance Orbiter, and Mars Express map the surface in detail, track storms, measure gases, and find ice. Their cameras can pick out rover tracks and show changes after dust devils pass. Each mission has a personality that grew from its work. Spirit felt like a scrapper, pushing until its wheels dug in and its power faded. Opportunity felt steady and patient, a marathoner that kept setting small records. Curiosity feels like a field lab that never tires of asking what, where, and how. Perseverance feels like a planner, caching samples for labs back home. The orbiters feel like quiet guards that see the whole. Together they have given us suns rising in blue, frosts forming on dunes, dust columns walking across plains, and cliffs layered with stories. They turned a red dot into a set of reachable places. Daily weather here would make any forecast careful. At the equator in summer, afternoon temperatures can touch 20 degrees Celsius on rocks that face the sunday. After sunset, they drop hard, often past 70 degrees Celsius. The swing comes from the thin air. With so little gas to store heat, warmth radiates to space fast. Winds can run to 100 kilometers per hour, but their push on a person is weak because the air is so thin. The dust they carry is the real concern. Small whirlwinds, dust devils cross the plains and leave dark tracks. Some are only a few meters wide, others reach hundreds of meters into the sky. Seasons are familiar in sequence because Mars's tilt is about 25 degrees, close to Earth's 23.5 degrees. They are longer because a Martian year lasts almost 687 Earth days. Summers are sunny but not warm by default. They melt carbon dioxide frost at the poles and shift the balance of gases in the air. Winters are long and lock more carbon dioxide and water into the caps. From time to time, planet-wide dust storms build. They do not sound violent, but they dim the sunlight for weeks or months, starving solar panels and changing the way heat moves between ground and sky. Between storms, the air can be clear. Daylight shows a pale sun. Night shows a deep star field. Sunset is reversed here. Dust in the thin air scatters blue light more efficiently near the sun's line of sight and lets red light scatter away. So the region around the setting sun turns bluish while the wider sky glows gold. The tone is soft and brief, and then the sky goes dark fast. A Martian day called a sol lasts about 24 hours and 39 minutes. The rhythm feels almost familiar. The content of that day does not. Heat and cold, calm and dust, light and thin shade trade places under an atmosphere that cannot hold heat and a ground that radiates it away. If you step one layer up from daily weather to long-term climate, you reach the deepest human idea attached to Mars: terraforming. At its most basic, it means thickening the air and warming the ground until liquid water can sit at the surface and people can live with less protection. The first lever is the atmosphere. Mars's current air is about 1% of Earth's sea level pressure and is mostly carbon dioxide. In theory, warming could release trapped carbon dioxide and water from ice and rocks, thickening the air and forcing a feedback. More pressure, more warmth, more release. Greenhouse gases could push the system. Orbital mirrors in fiction have aimed sunlight at the poles to speed melting. Big machines have fumed gases skyward in scenes that compress centuries into decades. Reality is slower and tighter. Measurements suggest that the accessible carbon dioxide on and near Mars's surface is limited. Even if all of it were released, the pressure might still fall far short of safe, stable levels. Without a global magnetic field, any new thick air would also leak to space over time as the solar wind and sunlight chip away at the upper atmosphere. The scale of effort to lift pressure, keep it, and manage side effects is beyond any plan we can build now. There are smaller steps. Instead of changing the whole planet, we can shape local environments. Paraterraforming builds controlled pockets, sealed domes above ground, or carved spaces below it, with managed air, water, and heat. Inside, crops can grow, people can work in shirt sleeves, and industry can run without suits. Outside remains Mars as it is. This approach fits the tools we have, though it lacks the romance of walking bare-faced under a Martian sky. It also respects the cost curve. A single, well-run habitat can teach lessons that move the whole plan forward without pretending to finish the job in a lifetime. The ethics matter as much as the engineering. If Mars hides native microbes in the subsurface, large-scale changes could erase them or change them beyond recognition. We would be swapping the only untouched Mars for a human-made version. Some argue that we have a duty to protect the planet until we know whether it holds its own biology. Others see terraforming as part of a longer-term survival strategy for humanity. Turning Mars from red to green is often framed as a backup plan. If Earth ever became unlivable, a warmer, wetter Mars could serve as a second home. That view treats the planet not only as a scientific target, but as insurance for our species. Set against it is another view that values Mars as it is: cold, dry, and ancient, a record kept in rock and ice that we should not overwrite. Between these positions lies a knot of ethics, ambition, and practical limits. Even generous estimates say that global changes would take centuries or longer. Over spans like that, our tools will change, our values may shift, and our needs may be different. We might reach a point where the capability exists, but the desire does not, or we might choose to adapt to Mars, instead of forcing Mars to adapt to us. For now, terraforming sits between possibility and fiction. It is a thought experiment made of physics and also of restraint. Mars has gone about its business for more than 4 billion years without us. Whether its next pages stay red or turn green will say a great deal about us. Long before spacecraft drew maps of dust, plains, and crater rims, Mars lived in stories. Its reddish tint was plain to the naked eye, and people connected that color to blood and battle. Romans named it for Mars, a guardian of the state and a symbol of military power. Greeks told of Ares, more chaotic and hot-tempered. In Babylon, it was Nergal, tied to war and plague. In Hindu tradition, Mangala linked the planet with strength and conflict. Even when not a war god, Mars carried an edge. Danger, energy, and resolve sat in its name across languages. As telescopes improved in the 1800s, observers began to sketch details, dark patches, bright caps, and lines some thought were very straight. Giovanni Schiaparelli called the lines canali, meaning channels. In English, that became canals, and the shift fueled a surge of ideas about engineered waterways. If there were canals, there might be builders. Fiction stepped in. H.G. Wells imagined a hungry Mars in The War of the Worlds, 1898, turning invasion into a mirror for the age's industrial reach and fear of decline. In 1938, Orson Welles adapted the story for radio. Reports of panic spread and the tale became legend, whether or not the fear was as widespread as later stories claimed. The point remained, Mars felt like the other, near, unknown, and possibly hostile. In the early 1900s, the dying Mars idea took root in pulp adventures. Edgar Rice Burroughs' Barsoom series drew a desert world of cities, tribes, and stark heroics. Later, Ray Bradbury's The Martian Chronicles turned Mars into a quiet stage for memory and loss, using the setting to reflect on human choices. Outside fiction, public interest swelled. Observatories opened their domes to lines of visitors. Newspapers mixed speculation with fact. Even careful scientists argued over whether the darkening of some regions meant vegetation and seasonal change. Each opposition the planet's close approach brought fresh sketches and debates. The fascination seeped into art and music. Gustav Holst's Mars in the Planets painted the warlike theme in sound, while painters set stark plains and twin moons behind their scenes. Mars became a mirror for the century's hopes and fears. Scarcity, expansion, the search for life, and the hunger for new places to go. Today, much of the mystery has been replaced by data, but the story power remains. The canals are gone. The questions are sharper. Mars is still a stage for our imagination. Now the scripts include sample tubes, landing ellipses, and return trajectories. The glance upward is joined by line items and mission budgets, but the spark that starts it is the same. In the next 100 years, Mars will likely move from distant point to familiar place. The planet itself may not change much. Our reach will. Agencies and companies are drafting plans that once belonged only in novels. Robotics will lead. Rovers will drive farther, work longer, and drill deeper. Sample return pieces of Mars in Earth labs could rewrite large parts of geology and past climate. Orbiters will watch frost come and go, track dust, and capture subtle shifts in dunes. Weather will be followed the way you watch a quiet field, noting the small changes that add up. Human flights will be the large step. A round trip might take close to 3 years. Crews would live in tight quarters, under steady radiation with no quick rescue. Entry, descent, and landing are a major puzzle. The air is thick enough to matter, but too thin to slow a heavy craft with parachutes alone. New systems must handle heat, deploy at the right moments, and guide vehicles to safe ground. If a crew lands, the next question is duration. A first visit might last weeks or months. A lasting presence requires systems that run for years. Water from ice or air, oxygen split from carbon dioxide, food from greenhouses whose heat, light, and nutrients must be tuned with care. Each is proven in principle, but doing all of them together, far from help, is the real test. Some plans imagine settlements under domes or inside lava tubes, with nuclear or solar power feeding lights and farms. Children would grow up there, learning about oceans and forests from books, screens, and trips home that few would make. For some, such a city is a hedge against disaster on Earth. For others, it is an expression of human restlessness, the strong pull to see beyond the ridge. There is also a quieter path. In it, Mars is like Antarctica, a place for research and careful visits, valued because it remains close to its original state. This path emphasizes protection. If native microbes exist anywhere, heavy human use could hide or harm them. An intermediate future is possible. Robotic bases could be permanent, sending samples and data. Crewed missions could be rare but regular. A web of supply flights could tie Mars into human activity without overwhelming it. However it goes, the relationship will become routine rather than rare. The red dot becomes a neighbor with a calendar. From Mars, Earth is a pale dot in a black field. Through a small telescope, you might pick out a swirl of white, a hint of continent, a tiny crescent of the moon nearby. Most of the time, it is only a point. On clear nights, the dot shines with a steady light. You can hide it behind a fingertip. In that speck sit every ocean and mountain, every city and voice. Distance makes the view both sharper and softer. Blue and white are plain. Everything else is implied. The gap between the worlds changes all the time. At the least, about 54 million kilometers. At the most, more than 320 million. Light takes minutes to cross it. A call might carry a hello, and a reply would not arrive until many minutes later. Conversation breaks into measured notes. Words become careful. The pause carries its own weight. From this distance, borders vanish. Nations are smaller than a pixel. Weather and cloud bands share the frame. The overview effect that astronauts describe in low orbit is amplified. Earth becomes one thing, small and bright. You also feel the absence of Earth's signs on Mars more strongly. There are no waves, no trees, no birds. The dot in the sky becomes a tie to all of that. Planners, study this psychological load. Homesickness on Mars is not solved by a free weekend and a flight back. Schedules, exercise, private time, and meaningful work will matter. So will a simple ritual, stepping outside, finding Earth, and remembering why you came. The view can comfort and sting at once. It tells you that home exists and that it is far beyond the next ridge. The view also teaches scale. In the solar system, Earth is small and lucky. From Mars, it is not the center of anything. It is one light among many. That sense of proportion sharpens care. A thin film of air holds the warmth and weather that make life possible. You understand, perhaps more clearly than ever, that stability is not promised. The site builds kinship with Mars as well. Two worlds, two stories. One warm and blue, one cold and red. both shaped by sunlight, gravity, and time. From Jupiter or Saturn, both would be little points in a shared sky. For those who work on Mars, Earth might become a marker of days. After checking panels or sealing a hatch, a person could tilt a helmet and pick out the blue glint. The dot would hold family, languages, and long memory. Its pull is strong. Humans learn the sky by the sun and moon, and by patterns that return each year. On Mars, those patterns shift. The same constellations are there, but clawed into new angles by latitude and season. Yet one familiar light remains. It says, "This is where your story started." Over time, home might change meaning. It could become the connection rather than a single place. Earth and Mars as parts of one path, one as the cradle, one as the workshop. Across the distance, the dot shines enough to find again. Silence on Mars is different from any quiet on Earth. It is not the hush of snow or the pause before rain. It is built into the air itself, or into how little of it there is. The moon is airless and silent too, but it is close and always shows a huge Earth in its sky. That nearness ties it to home. Mars does not feel tied. It hangs alone in thinner light, and the gap between you and everything living feels larger than anywhere else you could stand. Distance makes part of that feeling. The moon is days away. Messages arrive in seconds. Mars is minutes away in light time, even when the planets line up well. At the far end of the cycle, nearly a quarter of an hour can pass between a word going out and coming back. Chat turns into letters. You choose phrases, send them, and wait. The moon also offers a lantern in the sky. Stand on its surface, and Earth hangs large and bright, a steady disk you cannot lose. On Mars, Earth is reduced to a pale point. You have to know where to look. Even then, it feels delicate, like a bead of light that could disappear if dust blows or a cloud passes in front of the sundae. That alone changes the emotional weight of being there. Silence on Mars would not feel like an empty room. It would feel like a presence. Humans grew up in noise, voices nearby, water running, leaves moving, engines droning. Take that away, and the mind looks for anchors. On Mars, the land offers few. You could walk for hours and never see a living thing, never hear a bird lifting from a rock, never smell a flower or wet soil after rain. The air is too thin to carry much sound. What remains gets close. Your boots press grit. Your breath fills your helmet. A faint hiss from your suit lives with you like a second pulse. Sometimes, a breeze would slip over stones and wires. It would not roar. It would sigh and fade. Some would find that quiet heavy. Others would find it steadying. Without constant signals, the senses open. You notice the powder-soft layer of dust that plumes and settles in slow arcs. You count your steps without trying. Time moves at a calm pace because nothing here hurries. Seasons take twice as long as ours. Dust builds and lifts and builds again. Craters fill and are uncovered by the same wind over and over. If a place can be outside of human time, Mars comes close. It stood like this before any ear could hear it, and will stand like this when no one is watching. That knowledge can be stark, but it can also be a kind of rest. The mind needs rhythm, so crews would make their own. Music in a habitat, exercise at set hours, shared meals even when nobody is hungry, green lights on a small rack of plants that rustle the air inside a dome. Tasks break the day into useful pieces, checking seals, logging power, cleaning dust from joints, reading instruments. The work adds a human pulse to a place that does not beat. Over months, that structure is not luxury, it is health. The planet will not meet you halfway. You bring the pattern with you. It helps that Mars rewards attention. This is more than rock and cold air. It is a world that stores its history patiently, layer by layer. Every image, every spectrum, every thump on a seismometer adds a sentence to a long story. We read river paths in the shapes of dry channels. We read wind in the orientation of dunes and the glaze on pebbles. We read chemistry in colors and in how rocks warm and cool. The red hue comes from iron oxide, a thin film on grains ground fine by time and weather. The great volcanoes rose because the crust did not slide like Earth's. Hot spots fed the same vents for ages, building gentle, broad shields. The canyon system split because the crust stretched and failed. Then gravity and landslides and floods made the breaks wider. None of this asks for myth. It asks for patience. Questions crowd the edges of what we know. Was early Mars blue enough and warm enough to keep water standing for ages? Or did lakes and rivers come and go with bursts of heat? Did microbes take advantage of those chances? If they did, where are the traces, mineral patterns, carbon signals, small shapes locked in sediment? If they did not, why not? When so many of the ingredients seem right, methane sometimes shows up in breath-thin amounts. It could be life, or it could be rock reacting with water. It could be both in different places. The planet offers clues and then asks us to be careful with them. There is also a part of Mars that does not live in numbers. Sunsets that turn the near-solar sky briefly blue while the rest glows gold. Frost that paints a dune before dawn and melts into air by mid-morning. Two small moons that move so differently, one hurrying, one drifting, that you can feel the geometry of orbits in your neck. None of this is a result in a table. It is simply what the place is like. To study Mars is to weigh these two threads at once. Facts that fit into charts and moments that sit in the chest. Even then, Mars reflects us back to ourselves. Dry riverbeds on Mars echo the channels we know at home, and the comparison sharpens both. Layered cliffs here look like the ones carved by water and wind on Earth, and that lets us place events on both worlds in a shared frame. The loss of air on Mars turns into a lesson about shields and balance, and about how thin a margin protects a surface from radiation and cold. Every rover image of a far-off blue dot floating over a red horizon pulls the same string. From that distance, what matters about Earth is not its borders or our arguments. It is the thin film of air, the moving water, and the fact that life happened there and stayed. Mars also sets our pace. It turns, orbits, and shifts without regard for launch windows or budgets. Missions slip, then fly, then wait in the cold to take data when the sun is right. No schedule can make winter at the poles arrive faster or dunes migrate sooner. When a dust storm wraps the planet, cameras close their eyes and power budgets tighten. The delay teaches patience. The numbers in a lab back home may move with a deadline. The planet does not. If people do step onto this ground, they will not arrive alone. They will stand in the tracks of machines that did the slow work first, flybys that took the first close pictures, orbiters that mapped, landers that tested air and soil, rovers that climbed and drilled, a small helicopter that proved thin air can lift a rotor. They will count their steps in sols, not days. They will watch the sun circle low in summer at high latitudes and vanish for months in winter darkness. They will grow food in trays under light that hums and speaks to leaves in frequencies tuned by hand. They will recycle water until every drop has a history. They will hang pictures of family over hatches and know that reply times stretch across minutes, not breaths. All of this would press on the mind, yet the very distance that makes homesickness sharp can make perspective clearer. Look up at Earth from Mars, and you see the whole at once. There is no room in that point for noise. The view folds timelines together, the rivers cut in rock here, the river you grew up beside there, the years your crew will spend off-world, the billions of years the planet has already stood. Perspective does not remove risk or fix faults, but it can steady hands. Back on Earth, the view from Mars has already changed us. It has given us a planet-sized mirror and asked what we value. Do we take Mars as it is, reading it for all it can tell us and keeping our mark small? Do we try to make parts of it more like home and accept that doing so will leave permanent traces? Do we choose both paths in different places and at different times? The debate is not only about engines and polymers, it is about care and scale and time. There is humility in each option. To try to warm a world is to face immensity and limits. To decide not to change, it is to accept that some dreams move slower than lifetimes, and that patience can be a form of courage. A middle course, local habitats under domes or in rock, asks us to design good rooms rather than remake the sky. It trades romance for reliability and returns a kind of intimacy, a garden grown by hand in a place that would not feed one leaf without help. Mars keeps teaching even when we argue. It teaches that worlds are fragile. It shows how fast a planet can shift from wet to dry on cosmic clocks, and how some changes do not reverse. It teaches endurance. Dunes keep their ripples against long odds. A slope holds its angle and slides only now and then. Ice breathes in and out of the poles in a rhythm that never needs us to set it. It teaches that the basic ideas, gravity, light, heat, write a story that runs everywhere, and that what we learn from one world helps us read another. Distance adds a final lesson. The quiet here is not a lack. It is a kind of fullness that does not include us by default. When you stand in it, you can feel how rare life is and how lucky home is. You can feel how thin the shield over oceans and forests is, and how quickly heat can leave ground when there is not enough air to hold it. You can also feel that beauty and meaning are not limited to places that are easy to live. A curve of riverbank written in stone. A stack of layers that switches color every few centimeters because the wind was different that year. Frost that draws lace and then vanishes. These are small, but they add up. In the centuries ahead, our presence here may grow. We may build safe rooms in rock and light them with false days. We may train tomatoes to like a new air and set them to climbing strings. We may learn to mine ice without clouding the air with dust and to keep machines clean in a world that wants to coat them. We may map caves and find places where radiation is gentle and temperature swings are small. We may send children to school under arches of polymer and glass and teach them constellations that look a little off. We may, at the end of long shifts, walk out to a ridge and point to a pale spark and know that is where the stories came from. What will not change is the pace of the place. The red line of the horizon will still arc farther than it seems. The sun will still be smaller than you remembered the first time you saw it from here. The wind will still move with the same dry patience. Phobos will still cross the sky too fast, and Deimos will still take its time. Rovers old and new will still leave tracks that soften as dust returns. Some will sleep under that dust and keep their last views. Others will keep moving. Mars has been a teacher without a voice. It has shown us how to read landscapes for clues, how to build machines that last years longer than planned, how to accept unknowns without filling them too quickly with answers we want. It has given us a way to see home with fresh eyes and to name what matters there. It has asked us to hold two truths at once, that we are small and that our choices reach far. Stand with that for a moment. Listen to the thin air touch a rock. Watch a small cloud drift and disappear. Look down at a pebble that has not moved in a million years, and at your print next to it that will blur soon and then fade. Then look up and find the blue point. Let that be enough for now. The planet will keep turning under a pale Sunday. The shadows will slide and stretch. The wind will move dust from one quiet place to the next. And somewhere beyond the ridge and the long plain, Earth will glow as a tiny light in the dark and will wait for billions